So I'm going to focus on things that I think where being projective is is gives significant insights and gives new tools and so on. And I'll try to throw up some examples that illustrate that. So there will be questions that aren't geometric and which I haven't put in here. And there are other ones which are projective and still didn't make it in here because it turns out there's a lot. So I've got a short list there of some of the topics I hope to talk about, and I will, I think, pretty much explain them when I get to that point in the thing. So first of all, almost everything I'm writing can be written with just projective coordinates. Don't even pretend to be in the Euclidean plane or whatever. There's a long history of rigidity being done with projective points of view, and names like Mobius and Plucker and Grassman and Cayley and Klein all come up if you look at the history of that, and all of them did some things related to kinematics and mechanics and statics. And an interesting classic reference for a lot of the past stuff is a book you may not have looked at, Felix Klein, Elementary Mathematics from an Advanced Standpoint, Geometry. It was written for turn of the century German high school teachers, which means it's can be tough going for some of our graduate students just because of the difference in geometry background. And I've referred to a couple of papers that are in progress and where a lot of this is now being written. So there is a history. It's pretty natural. Statics is pretty obviously, to those who know both projective geometry and some statics, it's a projective theory. And Mobius knew that, and his whole stuff, if you look now at barycentric coordinates, weighted points, balance of forces, it's about statics. He was writing a textbook on statics when he developed barycentric coordinates. Rankine, about contemporary of Maxwell, was writing another textbook for engineers on statics, and he took one look at a talk on the quote new geometry in the 1860s and said, oh yeah, obviously statics is projectively invariant. And he wrote a 3-page note about that. So for those who lived in the geometric world when engineers and mathematicians and so on were the same group of people, it was projective, and it can all be written nicely projectively. In fact, more clearly in projective coordinates than in Euclidean coordinates. Because if you try to write the equations for a balance of forces in, say, 3 space, it's 6 equations. But by writing it in the projective coordinates as 2 extensors, you actually have the 6 coordinates, and all of the stuff sort of fills in more easily, and a lot of these statics is more easily done knowing it's projective. So that's a clean and effective way. It's not terribly common, but there are a number of articles that use that kind of vocabulary. And I can give you some more references if you ask. I haven't got the chat open, so tell me if I should. So here is something people aren't so familiar with. You think of infinitesimal motions in whatever dimension you are with projective objects. So centers of motion is the general context where you end up using projective points and lines and screws and whatever. And what I've illustrated here, if you can see it, I hope it's visible. If I give you the equation for a bar, that a bar should be the 2 velocities, VA, VB, should preserve the length of the bar. then I'm really saying that really saying that the two projections onto the bar line are equal, and that's the usual Euclidean equation you write down. But if you turn all the velocities 90 degrees, you get something I'm going to call in the plane the projective momentum. It's the projective form of infinitesimal motions. And there are a couple of observations to make there. One is that when I turn that, the condition about having equal projections turns out those are saying that equal after turning equal distance from the line. So it's saying that this line and this line will be parallel, and it's turning it into a statement that's more projective, which is it's a parallel. There's a parallel drawing going on of the bar, and that was mentioned in this morning in the talk. The parallel drawing is another way to look at it, and so you can write everything in a projectively invariant vocabulary, and the momentum. Well, in the plane, a momentum is a piece of a line through the point, and the length of it tells you its weight. It's the way the things are working. But if you're in three space, the general motions are screws, and the momentum of a vertex will be a piece of a plane through the point, and I'll try to illustrate a small use of that. But generally, working with the projective is quite useful in terms of insights. So let me give you a couple of applications where you may or may not see this. So a standard transformation or operation with frameworks is coning, where you take your framework in one dimension, in a dimension, pick a point one dimension higher, and connect that point to all of the points in your lower dimension. And this works between any two dimensions. And the thing about coning, let me just see, I think I've geometrically coning actually preserves all of the static and infinitesimal mechanical properties. The framework is whatever property in the plane, if and only if the cone is that in three space. And this is actually something I learned about sort of as from engineering folklore from a structural engineer I worked with for years, but I think it's become part of the operations we always do. And the not so immediate, but it's not too difficult, is not only do I leave the thing in the plane, but I actually am moving. I can move the vertices up and down towards the cone point, and none of the mechanical or static properties change. So coning is a very nice operation. If one of the things you can do, of course, is take the cone, do a Euclidean transformation in three space, and project back down. And again, none of the properties change. And that's actually a way to see that you can do projective transformations of a framework and not change any of its properties. So coning is going to be it's an operation we actually, what we're writing now, we're asking about coning for every kind of operation, every kind of structure you might have. Say the ones that were being looked at this morning about rods in the plane and so on. You could say, well, what about cones of those into three space, blah, blah. It just becomes a natural question and often gives you some additional insights. So this up and down is what I call a push-pull kind of thing. So coning is there, and it works in lots of circumstances. Then, are there any questions about coning or whatever? So for those who've been looking at the broader literature, coning also applies to bivariate splines and to lifting and to all of these other projectively geometric properties. And I'll come back to it, but if you think about this cone with all of the vertices pushed and pulled, you could think of them, say, carefully pushed and pulled so they lie on a surface of a sphere, and then you will be looking at rigidity on the sphere instead of the plane. Projective conditions. In general, when I have an isostatic graph and I ask when is it, for which special positions is it singular, then there is a projective polynomial that when that thing is, if that polynomial is equal to 0, then you're in a position where the rank of the matrix has dropped and there's an extra stress, an extra infinitesimal motion, whatever. So there's been a fairly extensive study of what are these polynomials like. If you look at the polynomial you got there, and I think I got all the things in the correct order, this is being written in what we call the bracket algebra. So these, each square, each little box like that is really to be thought of as a 3x3 determinant in the projective coordinates of the points. So it's as a plane circumstance. So if you look at that and look across it, this is going to be a condition about when 6 points lie on 6 points in this kind of K33. If they lie on a quadratic surface or a circle, then the polynomial will be 0. So look at the pure condition. You can look, it's 2 terms. A1, which is one of the points, it appears twice in each of those terms. The whole thing is quadratic in the coordinates of A1. The same with B1 and A2 and B2 and so on. It really is the expression of this is a quadratic or a conic in the plane, and that's what the polynomial represents. And there's a theory about pure conditions and so on. The one that's relevant here would be that that's an irreducible polynomial in your usual sense of algebra. There's no factoring that says if this small piece does something special, then it's degenerate. It's all or nothing. And sometimes pure conditions factor, but this one doesn't. And there are important questions about factoring or not. So so here is what happens when K33 is on a circle. And I'll first give you the Euclidean version, and then I'll give you the projective notation. So here are the velocities of the bipartite graph that turn out to be preserving at instantaneously the lengths of all of those edges when the points are on the circle. Namely, one class of vertices, all the A's are pushing out and all the B's are pushing in. So it's sort of an in-out motion. And that kind of motion happens anytime a complete bipartite graph or a subset of it is lying on a circle or in a more general quadratic. And why is that? Well, it's actually a simple thing. If you just look at a single bar on a circle, you're going along the rays from the center of the circle, and if you go in and out at the 2 ends, you get equal and opposite projections onto the edge. So that in-out motion is visible Euclidean terms, but it's even more interesting if you, well, there it is. That's not a projective way to do it. So here's the projective way to do it. Turn all of the velocities 90 degrees, and you look now, all the velocities that were radial, were perpendicular to the circle, are tangent to the circle. And the 2 classes of vertices, some are going clockwise and some are going counterclockwise around the circle. And if you look just what happened to a single bar, the way to think about this is that the two momenta, the two projective tangents to the points on the circle, they will meet in a point. That point is the center of motion of the bar. If that is the center of motion for the bar, then those are the two projective motions, and you could turn it back to make them Euclidean when you want to. But it's interesting. So if you know enough projective geometry, you might realize that the center of motion is actually the center of motion is actually the polar of the line in the circle, if you just do projective polarities. So that you're taking every line to its polar point. And you do that all around, and there you've got a nice map of going from the framework to the infinitesimal motion whenever you've got a circle.
So Walter, can I ask a question at this point?
Please.
So, okay, so suppose that I knew this very geometric perspective on this motion. Should I be able to understand this polynomial? Because the polynomial is like, how shall I say, a bit forbidding, and it's also only one representative of its coset, I guess.
It is.
And so
yes. So what you need to do, the translation, I was thinking about that last night. The translation between the two is Pascal's theorem. So how do you tell that 6 points are on a conic? Well, you write down some corresponding edges and say they must meet at points on a line. So you have to go through the projective geometry theorem but there's another way to do it, which is that polynomial will factor if you're working with the projective algebra which I would call the Cayley algebra, Cayley Grassman algebra. If you're working with that projective algebra of meets and joins and so on, it takes you right to that polynomial from the theorem. And if you work hard enough, you can go from that representation back to the projective construction. Did that help at all?
Okay. Yes, actually it did. So the point is that secretly there's a Grassman-Cayley factorization. That's a projective synthetic construction. And that would tell us about the conic.
But there can be pure conditions which we don't know how to factor. So if I go to the three-dimensional version and talk to you about K46 on a quadric in 3 space, there is no direct Cayley factorization of that into a projective construction. It's a 200-year-old problem to find a projective construction for testing whether 10 points are on a quadric in 3 space. It's somewhere embedded in the history of the Belgian Academy of Sciences. It's posed by I'm not going to get his name right, Charles. What?
Yeah.
So he posed that, and nobody has solved it. Turnbull sort of basically said, I don't think there's a factorization. He worked on it. So there, all you know is you've got this big quadratic equation, quadratic in all 10 points. So it's got 20 terms in 3 space, and nobody knows how to factor it except in kind of silly ways, silly ways being what Bernd Sternfels and I did. There must exist one, but yeah. So let me just make sure my thing wants to go to sleep, so I will bring it back. Why does it? All right, there it is. All right. Let me do a different projective transformation, which most people haven't really looked at. Let's think about doing a polarity of a bar and joint framework in 3 space. So the octahedron is a nice isostatic framework in 3 space. In the polar, every vertex goes to a plane. And every edge goes to an edge where now the two planes at an edge, the two planes at an edge meet in a line, and so you end up with plane sections and lines, and you can ask about the infinitesimal rigidity of this, where what's going on in the plane is, I don't know the details, but it's isostatic in the plane. It's some kind of equivalence class of triangulations in the plane of all of, and it's what I call a sheet. It's like when you make some polyhedra out of paper. At the edges, it's nice and firm, but all the way through in the middle, it's just sort of a little bouncy, and it's second order rigid, but not first order rigid. But if you think of something made of those kind of pieces, you get a nice kind of structure in three space. The only place you should apply forces is along the edges, not in the middle of the faces. And your entire theory of statics and kinematics transfers to these sheet structures. So there's a bunch of objects you can build and play with, and maybe when we get to the end, I'll show you some of my models. But so there's a nice theory of sheet structures, and you know about it from polarizing either the statics or the kinematics. And there's one paper published on that, and a lot of other notes, sort of not really finished, to take you through the. I see not all the typos got corrected. This is related to Alexandrov's theorem. So if I had left the corners in there, it would look like a cube. Cauchy's theorem says convex triangulated spheres are infinitesimally rigid. Alexandrov's theorem says if you've got any kind of convex polygonal surface and you triangulate the faces, then it's still infinitesimally rigid. And it allows you to do more. It allows you to throw in points along the edges and retriangulate. So there is some past history where people looked at these sheets. And the point is, the sheet is, if you think of a triangulated like square like that, no matter how you triangulate it, it's not infinitesimally rigid in three space. It's just rigid in its face. But that's all you need is those rigidities in the faces, and that's enough to get the whole thing. So it's an interesting situation. Polarity works nicely in three space. It doesn't work in a simple way for any of the other dimensions, which is curious. There is a theory about polarity in the plane, but it relates to something in reciprocal diagrams that I won't try to go into. And there's some theory about four space that's an extension of Alexandrov's theorem to higher dimensions, where like in a four space, you triangulate the two-dimensional faces of your convex polytope, and that becomes infinitesimally rigid. So there's versions that are worth thinking about. But what happens about polarity is a reasonable question. And I once more let my machine go to sleep. Okay. Change of metric. So here's the claim. Infinitesimal rigidity on the
So can I ask another question about polarity?
Yeah.
So there's another sort of thing that people do with polars of convex polytopes, which is they turn them into packings on the sphere.
Okay.
Right. So if you have a circle packing on the sphere, right, you can look at the planes, right, that cut out the circles and then polarize them, you get a polytope.
Yes. And the edge lengths in one circumstance become angles in the other one.
That's right.
So it's an interesting theory that where lengths turn to angles in hyperbolic or spherical. And there are some, so essentially one version of Cauchy's theorem becomes Andreev's theorem in hyperbolic space in terms of uniqueness of angle patterns. So there is another whole theory, but it's not polarity in Euclidean sense, right?
That's right. I mean, you need to, right. So when you do that polarity, you also change the objects that you look at, and then they have a different natural geometry.
They do. And it's nice and it's worth exploring. But that's the point. There are other directions to go with this. So change of metric. If I have a framework on a plane and I make that plane tangent to the sphere, I can suck that framework onto the sphere and it will have exactly the same infinitesimal and static properties on the sphere. And essentially it's on a cone to the center of the sphere as it did in the original plane, or vice versa. So everything you know about rigidity in the plane applies, at least at an infinitesimal level, on the sphere. And it turns out also on hyperbolic and Minkowski for that matter. So the ability to change metrics in this context has to do with looking back to Cayley's characterization of the metrics that come from projective geometry. So Cayley's Erlanger program and all. But just to say, sphere and plane are projectively equivalent, and there's simple transformations of the one to the other in any pair of dimensions. Here's the local thing you do, just if you're wondering. If I know the velocity on the sphere, it will be tangent to the sphere. You simply push it out from the vertex you're interested in. You push it out from the vertex you're interested in to the plane you want to, drag along the other end of the velocity parallel to the original, and then project onto the plane. And that is the projective transformation that takes the velocity of one to the velocity of other. It's a clear geometric statement. And so that a similar thing happens with hyperbolic, and I decided not to try to do that, partly because I didn't find such a nice picture. This picture comes from one of my students' theses who became relatively expert with GeoGebra and producing these kind of pictures in ways I'm not.
So could
yes.
I ask, so what exactly extends to hyperbolic? I didn't get that.
If I take my plane and I essentially go out the cone rays and put a hyperboloid in there, and project the points onto the hyperboloid and work with bars on the hyperbolic surface, infinitesimal rigidity goes to infinitesimal rigidity, statics goes to, all of the theory is identical in hyperbolic space. And if you're willing to play around, it's the same as true in Minkowski. So it's just that the entire theory is the same. And so one of the conclusions would be you're not going to get new insights into, say, rigidity in Euclidean 3 space just by changing metrics, because it's not any different. You're going to have exactly the same problems you did before. So in a sense, unlike when Sean was talking yesterday, you're not getting any change in the theory. Occasionally you get a different geometric vision for what's going on, but don't expect to solve 3-space rigidity by switching to another metric that is based on projective geometry. So in that sense, it's a negative statement. Same, that's it. Is that an answer?
Thank you very much.
Let me give you just a couple more examples where you may look at something and say, I don't see anything projective going on. And I want to encourage you to say, well, yeah, actually there is. So a standard 1-story building, you have your nice roof, you have a bunch of pillars holding it up. You may have some wall braces, which I've omitted. And the point is, I look at that and I say, it's a cone. All those parallel pillars meet at a point at infinity. I want to know what to do with the roof. I should just project it into the plane. So I should take my knowledge about cones and whatever and say, oh, I'm seeing that in a one-story building. It's not, nothing's changed. And so part of it is that you would look at something and say it's the same geometry. Here's another example where you might not see a lot of projective geometry. This is a standard truss that's put in the roof of shopping centers. Buckminster Fuller patented it as the half octahedral tetrahedral truss. And so I'm not sure, you may be able to see some half octahedra in here. Whoops, I didn't intend to do that. Okay. So yeah, there's some half octahedra here, and I seem to have gone beyond my capacity to modify the picture. If I have to, I'll go to a different. All right, so there's a tetrahedron, a line on the bottom, a line on the top joined, and here's a half octahedron. And there's one in the back. So there's a square on the back, and then a cone to that. So it's a bunch of these things tacked together, and you look at it and you say, I don't see projective geometry yet. And I'll show you this picture and say, oh, the lines on the top are a ruling of a top plane. The lines, the bars on the bottom are forming lines on a second plane. Those two sets of rulings of the two planes share 2 points at infinity. So this is really a ruled quadratic surface, 2 planes. And now you join whatever you want on the top and whatever you want on the bottom. And this is an extended bipartite framework. Bipartite framework with edges added that are part of the rulings. And this infinitesimal rigidity of such ruled surfaces with the and the bipartite graph on them, it's a well-developed theory. It comes essentially from extending Volcker-Roth's sort of stuff. So this thing will have infinitesimal motions, and therefore this will have at least one infinitesimal motion. And you might wonder whether that matters. And I'll just give you a glimpse. Let me see if I can make this any. So that's one of those kind of things that was the roof of a arena in Hartford Coliseum, and that's after it collapsed under a snow load. It was a near disaster because thousands of people had just left the stadium a couple of hours before. Again, it didn't. What's projective geometry got to do with the collapse? Well, actually, it collapsed because of bad engineering design. And the people who were living with it, like the people who had to walk through the rafters they knew it was failing from the moment it was lifted off the floor, off where it was constructed. But it does matter to the analysis. How did it fail? This looks like it's got fourfold symmetry, right? You might sort of see fourfold symmetry here. But in fact, the infinitesimal motion is a warp towards a parabolic hyperboloid where 2 corners go up and 2 go down. And so a symmetric failure is unlikely to be what happened. So it may get the wrong analysis just because you don't know your projective geometry. It doesn't predict the kind of stupid mistakes the engineer made. So here's another example. So you may recognize that as a the kind of hinge that you have in a window you can lift and raise. And when you do it, there's some sliders going on. So we're back to sliders, which came up in some previous talks. And we think of those sliders as points at infinity. So that mechanism of an engineer can be reanalyzed as a bar and joint framework with one slider, that's the red line, and you get the correct prediction of its infinitesimal motions, and it turns out to be finite motions. So if you want to understand sliders as a mechanical engineers do it, and you find them all through their textbooks, looking at it projectively and saying, oh, I've just got a few points at infinity, and I can continue to, and points at infinity are like points on the equator of a sphere, and I can project it down. So you can take the theory of plane bar and joint frameworks, and or 3D ones for that matter, and apply them to the mechanical engineering slider sort of things. And so that's the point. You look at it and you say, oh, there's projective geometry going on there because that's a point at infinity. And that sort of changes what you see. You start to look differently at things. And that's part of what I wanted to say, help you look at things and say, oh, I see projective geometry when you look up at the roof of a shopping center and you say, oh, I see a ruled surface, I see. And that's part of what I would hope that you would sort of start to look differently. And this theory of sliders and so on actually has some theory that goes beyond what was mentioned this morning, which is where you've got a significant number of collinear vertices, not just 3, but there's an extension of that theory, which is in the work now on sliders and so on, for an unlimited number of collinear points. And you then think about which of those angles are fixed between sliders and which are not. So there is a theory that applies to projective theory that applies in mechanical engineering. And some mechanical engineers are quite happy to say, oh yeah, this fits what with everything we know. By the way, if you end up talking to a mechanical engineer, they have a different counting thing they do than Lemann's theorem. It's called the Grubler, and they have another name attached to it, count. And it isn't quite as complete or efficient as what we do with our frameworks, but this is a way that mechanical engineers also analyze the things they have to build. Okay, other projective constraints. Yeah, I just don't want to go too long. I want to leave lots of time for more conversation. So liftings. There's other kinds of constraints besides distance constraints. So if I'm in scene analysis, computer vision, I show you a picture in the plane with some points and some edges surrounding things I've called faces, and say, how many ways how many three-dimensional objects could project to this picture I'm looking at? And it turns out that picture theory, that has a full theory all worked out in terms of combinatorial, at least. It's not expressed in terms of graphs, but in terms of incidences. And so I've just stated the theorem here that would predict how many different liftings does this picture have. And so this is a nice theory. It can be applied in lots of circumstances. It originally came from a conjecture of a computer scientist in Tokyo, Sugihara, but this is the way the theorem sort of reads. And so it can be used to answer some questions. One of those questions will come up on Thursday when Bill Baker poses his questions about what's going on with framework shells, sort of concrete shells for buildings in 3 space. So this is relevant to another talk that's coming up. I thought I should just at least put it in as a clear statement. there's another version of that, which is it turns out liftings from the plane to space, or any pair of dimensions actually, it's exactly the projective dual of the theory of parallel drawings. There is no difference. Every theorem in one goes to the theorem in the other, etc. So this is polarity taking your vision between two theories that started off looking different but have exactly the same combinatorics, geometry, etc. And so I'll give you the picture theorem in terms of parallel drawings in an arbitrary dimension. And here you're going to, I'm simplifying it to a graph. You're going to tell me this edge has this direction. So in the plane, that's one constraint. In three space, direction for an edge is like a point on the sphere. It's two constraints. In four dimensions, it would be three constraints. It's a complete theory for parallel drawings in all dimensions. In d equal to 2, just put in d equal to 2 into that, and you are looking at essentially a version of Lemann's theorem, because there's d minus 1 copies, which means one edge. And so this picture theorem gives a different proof of Lemann's theorem. No inductions, just a straight up take this matrix, muck around with it, do a little truncation, and there it is. So parallel drawings is a nice theory. It's projective. It connects to, in the plane, it connects to rigidity in higher dimensions. It gives you a really nice theory that would have all of the properties we've been talking about so far this week about, oh, this matroid is maximal in this count, etc. And it's a candidate for being carefully looked at. And I say that because, as far as I know, there's only a few papers on parallel drawing, and most of them are not published. And so I can send them to you, but it's a theory worth exploring. It's in some depth to figure out what's the best versions of it. It is a projective theory. It will have singular positions. It will have pure conditions, all of that. And it has multiple applications. So here's something, you parallel drawing of a convex polytope, that's a convex polyhedron, that's related to how many Minkowski factors there are of that polytope. So Minkowski decomposition is related to parallel drawing, and that's something that has been known by a number of the workers in the field. And it's not obvious, but Minkowski decomposability, at least locally, is a projectively invariant property. Not Euclidean, not affine, but projective. So let me, I think that's probably, all I wanted to try to entice you with. Yeah, so it does connect to rigidity in the plane and reciprocal diagrams. And I think we're getting a talk in another day or two about reciprocal diagrams, which are part of the old history of rigidity that only some people currently look at. But it is something that the engineers continue to look at, and which we're getting a talk about later, talking about what's going on with graphs on a flat torus and things like that. So lots of connections and things that could be done in the future. And I think I had hoped, and I think it's still time, we can see, do other people have questions or connections or new research problems that come to mind when you think about, oh, it's projective, I might apply this transformation, I might apply that. That's what I would like you to at least think about new questions. I've got a couple more buried later but let's see if there's any comments from you, and I can write down any comments you may have that.
So I have a question about what you were saying about how when you cone, like through coning, basically anything you can say in the Euclidean plane, you can say in like any other space that has a metric.
Or in the higher Euclidean space.
So, okay. So does this apply to symmetry too? Like,
I will show you a slide on symmetry. A couple, let me hold that. I do have something because it is an obvious question.
Okay.
And there is a paper by Bernd Schultz and I on coning and symmetry and going between the metrics. It turns out to be fairly straightforward, although of course you don't have exactly the same symmetries in each of the spaces, right? It's a local, but yes, it's yeah. But the coning isn't, you can do the transfer among metrics without knowing about coning. Is just a lot more obvious if you do. Right? In principle, you can just write down some equations and transfer, and that's there's a school of Russian geometers, Pogoyelov and Efimov and so on, who did write down some very large equations for some of those systems going from sphere to hyperbolic to, and they were interested in transferring failure of global rigidity between the various projective spaces. And it's there, and there are some books that have been translated into English that have a fair amount of that kind of stuff if you want. But I find the projective vision convincing and helpful.
Cool, thanks.
Other questions? I didn't entice anybody else to think about.
Sure, so I was going to ask, so in the Euclidean world, we have like a wide sort of variety of notions. We have like infinitesimal flexibility, but also finite flexibility, and we have global rigidity and so forth and so on. So my understanding is these are like a little bit more delicate, right? Like if I think about moving to say the hyperbolic plane, there isn't this obvious notion of like affine invariance, for example, right? So a lot of the tools and ideas we use.
So I think there are a couple of answers. Yes, this is projective, the pure projective is a little more delicate, but as you pointed out in a conversation yesterday, global rigidity is projectively invariant, give or take what's going on at the plane at infinity.
Right. Yeah, so up to some mild conditions, we are in good shape because of the way coning works.
Right.
Right, even universal rigidity is not so bad.
Right. So it's a surprising amount still has a projective error. Something that doesn't, if I've got something with a finite motion and I take a projective transformation, there's no guarantee that the new object has a finite motion. And the classic example of that, if I can get it all up. Oh, I'm still getting used to this. So if I do K33, for example, or KMN for that matter, on two perpendicular lines, it's always got a finite motion. But as soon as you make those lines not perpendicular, it's only an infinitesimal motion. So just that affine transformation changed you from infinitesimal motion to finite motion. And the whole question,
Yes.
When do I get finite motions? And there are classes where you do in fact get projectively invariant finite motions from particular kinds of realizations. And I think there's a bunch of those that have not been well investigated about in sliders. With sliders, you can get what would have been an infinitesimal motion to become a finite motion. And some of those, I think, are unchanged by projective transformations. And that by itself is a whole interesting topic. What isn't so obvious, if you do like a cone and your original thing in the plane had a finite motion, the cone has a finite motion. Not quite so obvious, but build yourself a few models and you realize why that is going to be true. So there are interesting questions of that type. And that's a topic that it came up implicitly this morning, because I would say these bracing of the parallelogram tilings and so on, that's really about parallel lines and points at infinity. And if you do a projective transformation, that's going to be destroyed. But let me leave it at that. Other comments, other questions?
So when we go from the sphere to the plane, we can project and we preserve infinitesimal rigidity, but we don't preserve finite rigidity, say. And the same is true for the hyperbolic plane? Am I correct in saying this?
To a surprising extent, you do preserve finite rigidity. And the way I think about sliders, by the way, is if you think about the hemisphere, the points on the equator are going to sliders. That's all it is. Sliders are like, I know what the normal to these lines is, and that one is a vertex like any other vertex. And so sliders are incorporated into this as a particular kind of projection from the sphere to the plane. And that's how we proved some of the theorems about sliders and so on, was by carefully projecting from the sphere to the plane.
Okay, so what I was going to ask was, so there's some issues projecting to the plane, but if we just project from the sphere straight to the hyperbolic plane,
yeah,
is there less issues then?
Well, so interestingly enough, when Pogoryov wanted to write up his global rigidity transfers, he started with something on the sphere and then took it to the plane and to hyperbolic. He thought the sphere was the natural place to start. And if you're ever in the library at Oberwolfach, there's a nice English translation of one of his books. They're in the library talking about exactly this kind of global rigidity. So the global rigidity transfer is a two-part thing, one of which is infinitesimal motion in one goes to infinitesimal motion in the other, and the other is that averaging in one can be converted to averaging in the other.
Okay.
It's not a project, you don't projectively transform the averaging, but you say, oh, there must be a pair of averaging things going on because there's an infinitesimal motion, and that will give me my failure of global rigidity. So it's all sort of clustered together in that Russian school of stuff. So the Russians had a large, another thing we haven't talked about is there's a whole area where we can look at differential geometry and rigidity in differential geometry in the various contexts. And when do you get some insights into the discrete structures coming from differential geometry and vice versa. So a bunch of the theorems involve limits of polyhedra going to a differential surface. And there's a polarity thing you do like I did for the sheet structures for in differential geometry. I think there may be one paper that sort of does that, but it's a interesting thing, and not too many people have spent time exploring them. I'll stop there. I could go on forever.
Well, thanks for that.
Let's get this. Okay, any other comments? I have another blank page. And then I'll get to the ones I anticipated. So let me wait to make sure whether there's
I just
any.
want to pipe up. So global rigidity itself is not even an affine invariant at a specific framework. So it's certainly projectively
Yeah.
invariant.
Sorry, you said global rigidity? No.
Yes.
So I think there are questions about global rigidity, and they were coming in a couple of pictures, a couple of slides from here if I didn't. Oh, I guess I ended up with the wrong version here. So here are some questions related to global rigidity. Can you apply global rigidity to a framework that's got points at infinity, that's got sliders? How does it extend when it gets out of the finite Euclidean plane? And I think there should be some global rigidity results for frameworks with sliders. Sheet structures. I don't know whether there's a global rigidity theorem for sheet structures. And by the way, there's a variant of sheet structures where it's just points and sheets. It's an self-dual kind of points. Points would polarize to sheets. Sheets would polarize to sorry, points would go to sheets. Sheets would go to points. And so there's this collection of objects in 3 space where all you've got is points and an assertion that for this particular combination of vertices, there is an infinitesimally rigid framework, including those vertices in the plane. And you can continue to try to do that theorem. It doesn't actually help you do 3D rigidity anymore, but it makes for a geometrically interesting sort of combination. So I have a lot of questions about sheet structures, and one of which would be, is there a version of global rigidity for them? What happens to global rigidity under polarity effectively? And I did promise to, whoops. I did want to, so symmetry and projective geometry. So here we are. If you've got a framework in the plane with a mirror symmetry, there's a projective transformation of the entire framework where that mirror goes to infinity and a point at infinity comes to the center of your diagram, and it's now a half-turn symmetry. So mirror symmetry and half-turn symmetry are interchangeable under a projective transformation in the plane. And the way you see this is if you go to the sphere and you have your mirror on your sphere and you've got the normal to that mirror, which is points at infinity. And now you do an antipodal map on the sphere, which projection nicely handles. And you say, oh, half turn and mirror symmetry are identical if you're living in, say, the elliptic model of the projective geometry of the elliptic model. So the sphere with antipodal points identified, those are the same symmetry. There's at least one chapter or more in a book of Conway on pairing and combining various symmetries in the elliptic geometry, in projective geometry. And so a whole lot of symmetries turn out to be the same thing. One's a projective image of the other, which is not what you might have thought about. I see Daniel sort of saying, how can that? So there, if you think about this, if you think about a sphere with a mirror, the the mirror operation takes the one normal to the other normal. So the normal is effectively fixed under inversion, right? And if you do a half turn, so if you do sort of half turns on the sphere around that axis, all the points on the mirror go to their antipodes and are fixed. So the fixed points of the mirror are intimately connected with the fixed points of the half turn and vice versa. And so it's not surprising that you end up with exactly the same theory of symmetry. And so there is a paper by Bernd and I and Tony and Katie Klitsch on this idea that you can pair symmetries and get new information by doing effectively projective transformations of one symmetric situation to a related one. And once you know to look for it, you can actually see something that's happening in a model with a mirror symmetry and the companion model with a half-turn symmetry. And there are some pairs of those examples which didn't survive my downsizing from my office, but which Bernd has. But in general, can you, yeah, so I had a couple of questions about global rigidity, one of which would be what happens with sliders, what happens with sheets. So, and something that didn't come up here, but may come up when people are looking or thinking about, say, Sinichi's talk or whatever, there's the entire theory of bivariate splines. That's also projectively invariant. That also has projective transformations. It is not the projective transformations of 3D rigidity because the frameworks live in the plane, but there is a full projective theory and a combinatorial transfer, well, conjectured transfer. Remember, the bivariate spline matroid is actually the maximal matroid for 3V minus 6. And it's got projective properties, and those are of interest to people working in approximation theory. So that's yet another direction. And when you get a hold of this paper we're writing, we will include a section on the bivariate splines as well, because there is the projective theory and the projective operations. Oh, one obvious question about coning would be, what happens if you cone a rod framework in the plane into 3 space? Well, then you would end up with what had been a line becoming a piece of a plane, and it will actually, that's the question, it would behave as a plate in 3 space. And so you have plate and hinge frameworks, the pins between 2 rods become hinges between 2 plates. And there is a good theory of plate and hinge frameworks in 3 space. It's a nicer theory, more complete theory than the rod and pin frameworks. If you have in the plane, you have a line with a tree of edges, but it's not forced to be a rod, then the coning makes it into a sheet. So there are interchanges among the various theories that are useful, and I didn't go into it, but the whole theory of body hinge frameworks is very nicely projected and is connected to a fair amount of work that's going on protein modeling and those kind of biological applications and so on. They come out of working with body-hinge and polarity. That's where the original conjectures and theorems came from. It looks like this is where I should stop. Nobody's got questions. I didn't do a good enough job.
I have a question.
Oh, good. Yeah.
So you mentioned the failure of polarity for rigidity in the plane and also in other dimensions except 3. So could you develop that for the plane?
So for the plane, think about centers of motion. So in the plane, a line has a center of motion, which is a point. Right? Any rigid body in the plane will have infinitesimally a center of motion, which will be a point, finite or infinite. Yeah, that's the either rotation or translation. Now, when you polarize that, the center of motion for, and a point is being polarized to a line. And the projective center for that will project to a point on the line. So what you end up with is a bunch of woven, so a bunch of lines in the plane woven together with sort of this must stay connected, that must stay connected. And the motions you're now looking at are points on the line that are really, if I try to rotate this line up into 3 space, that's where it rotate about. And your infinitesimal constraints where 2 things meet is that those 2 lines must rotate up into 3 space around the same line. So it's liftings of lines into 3 space. The theory of lines in 3 space and when they intersect and how they cross, that's the theory that comes from the dual of plane rigidity. And it has, the theory is the theory of Lemann's theorem. It is answering interesting questions. They usually ask them corresponding to tensegrity frameworks, which is where I'm just told this line must be above the other line. I don't know how far. And so tensegrity relates to, oh, I've got a drawing of lines in the plane. This went over, this went under. Can I separate it into lines in 3 space that, where they don't cross, they don't whatever. So there's an entire theory about lifting of lines into 3 space, which several people, when working on that, detected that they were doing Lemann type counts, and in the end, it was projectively Lemann's theorem in the plane. So that's the theory. If that is that of any, is that any kind of answer? So there is a theory, and there are some publications of it called Rigidity and Polarity. I have 2 papers, one of which is about sheets and one of which is about this lifting of lines into 3 space.
Thank you very much.
More than you wanted to know. But that was a question of combinatorial geometers, or of people who were working in discrete combinatorial geometry of what are the patterns of lines. When, if I show you this pattern of lines that this is over and this is under, when are you stuck in the plane, right? It's called popsicle stick bombs. Start weaving together popsicle sticks and see if you take your hands off whether it explodes or whether it sits nicely in balance in the plane. And that's the theory that's just underneath the surface of the polarity in the plane.